So we're going to start with the very last review before we actually get into repeated measures ANOVA, and that is talking about two-way ANOVA, because one-way ANOVA wasn't complicated enough for us because we're cool like that. So a two-way ANOVA or three-way ANOVA, or however many way you want, ANOVA starts the same as the one-way ANOVA. You're going to see, if you do it using SAS, a table that looks very much like this. It's going to give you your model degrees of freedom, your sum of squares, mean square, and F value, probability F. It's going to give you the error, which is the within group sum of squares. And down here, you're going to see an R square, which is the amount of variance explained by your whole model. Over here, it gives you the mean. So you can tell that unlike last time where it was the mean with all of them standardized, here it's the raw values. Not that that matters at all. So sum of squares, mean square, F value, probability, R squared. 11% of the variance in the dependent variable, which happens to be how insecure they were at school, was explained by this model. What was this model anyway? Okay, well, this particular model added on to the one that we talked about last time. So we had, first of all, the level of the school, which is elementary, middle school, or high school. And that was very highly significant over here. It had a very large F value here. The next thing we had was the size of the school, which was broken down into four levels, right? Which is why we've got a degrees of freedom of 3. So basically there were small, medium, large, and very large schools. And then we have the interaction effect, which is to say, was there a difference of school size effect across levels? Did having a large school make more of an impact for elementary school students, say, versus middle school students or high school students? Over here, you see that the interaction effect was non-significant. The F value for the interaction effect was very low. So what this is telling us is that level, elementary, middle, high school, has an impact on how insecure students feel. The school size, large, small, medium, large, very large, has an impact on how insecure the students feel. And those impacts seem to be the same across levels. So in other words, having a bigger school makes you feel more insecure whether you're in middle school, elementary school, high school. Now, there are 4 types of sums of squares. If you didn't know, now you know. And they are type 1, type 2, type 3, and type 4. Usually, by default, you will see type 1 and type 3. Now, the important thing to know is that the type 1 sum of squares is order dependent, where the type 3 sum of squares is not. So since the interaction effect came in last here, this was after accounting for all of the other variables in the model. Down here, each variable, we're looking at the effect accounting for all the other variables in the model. And so the last effect is always going to have the same value. Let's talk about Venn diagrams, because that might explain a little bit about the shared variance and why the type 1 and type 3 sums of squares would be different. Here, let's say we have a dependent variable. Could be how insecure you feel. And we have an independent variable. Say the level of school, elementary, middle school, or high school. So we'll call that variable A. And here we have the variance of the dependent variable explained by A only, explained by our one independent variable. All right, now we have a second dependent variable, but we're just looking at them individually for a second. So our independent variable over here, say school size, explains some of the variance in our dependent variable as well. So this would be the variance explained, the variance in common between, say, school size and the dependent variable of how insecure you feel. Now, let's put them both together. And what we might see is some overlap. In other words, high schools tend to be bigger than elementary schools. So there's some common variance. Kids in high school and bigger schools tend to feel less secure than kids in elementary school. But the high schools tend to be bigger. So which is it? We don't really know. So this is common variance. So this overlap here, this thingy right here, this thing in the middle, that's the difference between the type 1 and the type 3 sums of squares. In the case of the type 1 sum of squares, whichever variable comes in first, A or B, sucks up all of that common variance. It gets it all. So you can change whether or not something's significant sometimes by changing the order, which is a very sneaky thing, and you should know that that's possible. Personally, like most people, usually look at the type 3 sums of squares, which is with everything already considered in the model. And also sometimes I vary the order, because what I want to know is, will my results come out significant and show, say, for example, that school size is important, regardless of what order I put things in, of what variables in the model. So, useful things to know: in the type 1 sum of squares, order matters. Something can change from significant to not significant by changing the order that you put it in your model statement. The type 3 sums of squares, order does not matter. Now, if you wanted to code it, it's quite simple. Proc GLM, data equals the dataset name, class, the categorical variables that you have, model, the dependent equals independent 1, independent 2, and if you want an interaction effect, independent 1 times independent 2. Okay, we're going to start with analysis variance, but perhaps not the way you think. We're going to start off with a libname statement. And my question is income related to spacing children? So here we have a comment. You don't need 3 asterisks, just 1 asterisk is sufficient. Put whatever your comment is in with a semicolon. Comment. Libname, my data. There's my reference to the directory where my data are kept and the directory for this course. Proc freak data equals my data.india, tables, FP3C and ED2, which if you look here, ED2 is whether or not the person was literate, and FP3C was the time they wanted to have their next child. So there are 3 categories. If they want to have their child within the next 2 years, after 2 years, or it's up to God. They don't have any preference. Notice something here. This is really super duper duper important. There are only, out of the 39,000 people, less than 8,000 of them that you have here. So you've got 2,000 for 1 year, less within 2 years, 2,600 for after 2 years, and about 2,000 that say up to God. So this is only asked of women who are of childbearing age, who's had children within a certain amount of time. So when you generalize from these data, you need to mention that. Not that it's not from the whole 39,000. It's only from a very specific subset of that. Now, I'm going to do a proc freak. I have tables, and I'm going to specify the 2 variables I want, the family planning question and the literacy question. I'm also going to do a proc means. Data equals my data.init var income. So by giving it the var statement, it's not going to do every single variable in the data set, but just this one variable. I'm also, for a reason you will soon see, going to do a proc univariate, data equals my data.india. Well, let's do the first 2 first. Okay, click on our little running guy here. Okay, completely as I expected because I looked in the code book. There are almost 33,000 people missing data. I have a total of about 6,600 people. For literacy, there's only 3 people, so almost everybody answered that question. Now look over here. Almost everybody, in fact, everybody answered the income question. The mean is 137,952. This is rupees, not dollars, okay? The standard deviation is 222,895, and the minimum from about negative a million to 11 million. That seems like a pretty darn skewed distribution. Just to be sure, I'm going to run a proc univariate. And I do. And the two things that I'm interested in here are the kurtosis and the skewness. Now, a normal distribution has a skewness of 0 and a kurtosis of 0 with SAS. So if you have a kurtosis of 502, that's pretty darn high. So a normal distribution is sort of like this. I can't really draw it here, but you know what a bell-shaped curve looks like. You know what skew looks like. Most of the distributions on the left side or the right side. And kurtosis is either it's really flat or it's really peaked. So this is a very non-normal distribution. We've got a lot of outliers in here. So I think what I'm going to do is I'm going to go back. I'm going to create a new data set, call it example. I'm going to have set my data.india. I'm going to read in the Indian Human Development Survey. And I'm going to only keep it. This is called a subsetting if statement. If income is greater than 0 and income is less than 432,000. Now, if you look over here, less than 0 would be, if it's 0, it would be higher than the top 1%. If it's less than 432,000, it'd be lower than the top 5%. So I'm going to cut out the outliers. I'm also going to put in, I'm only going to keep these three variables that I'm interested in here, the family planning, the literacy, and income variable. And the label statement is not required, but I use it a lot because I often won't remember what the heck was FP3C or ED2. So the label statement is just going to give a label when it prints out of FP3C is going to be next birth, ED2 is going to be the mom's literate, and income is going to be household income. Okay, so now let's run this with my remove the outliers, and you could see that the kurtosis went down from 502 to 1.76. So just dropping off those extremes made a big difference. The skewness went down from 14 to 1.45. So it's not 0, but it's far, far closer to a normal distribution than before. We have really eliminated some major outliers. So I feel good about myself, because those outliers can have a major impact on your results. Now, there are times, I just want to mention this, when eliminating outliers might be the complete wrong thing to do. If you're doing a business application, say, and you completely eliminate the people who make $1 billion, like I run a startup, right? So people are really interested in those that make $1 billion. You also would be really interested in the people who fail. In that case, perhaps ANOVA is not the best solution. And so it's a really good thing that in a few weeks we're going to cover logistic regression. So for now we have dumped our outliers. We're going to do a one-way analysis variance. So I've got these three groups. I'm going to have model income, which is my dependent, equals which they prefer for family planning, less than 2 years, more than 2 years, or let God decide. And I'm going to also ask for the means for all three groups at a Tukey. So I run it. And this tells me there are 3 levels, which I expect, that there were 37,000 observations, but only 6,000 of them are used, which I know because it's only the women who are of childbearing age who have already had a child within the last few years. They didn't ask this if you were like 75, because obviously you were not having a child. Well, here my model sum of squares is very large, but my error sum of squares is also very large. This is in scientific notation, right? So there's another 13 places out here. My F value is 0.76. Not very large. The probability of an F value that large is 0.46. So about half the time I would get an F value this large, just by chance. The R squared is way less than 1% of the variance in income is explained by which of these three groups you are in. Whether you're looking at the type 1 or type 3 sum of squares, it doesn't matter because there's only one variable in here. This chart shows me the graph, the means, and it's not like it was non-linear that one group was much higher than the other and averaged out. No. They all look to be pretty much the same. There are a few outliers here. The means are about the same. The medians are about the same. And remember we looked at the post hoc test before? Well, here, the difference between means between group 2, the people who said more than 2 years, and the people who said let God decide, was 2,787 rupees. Between group 2 and group 1, the people who said within 2 years, more than 2 years, less than 2 years, is about 2,900 rupees, which again is not that much money. So, yeah, nothing. Comparisons significant at the 0.05 level are indicated by asterisk. Nothing is significant, which makes perfect sense given the F statistic we had that showed that the difference between means is highly likely to have occurred by chance. Okay. Let's do a different one by ANOVA. Let's look at literacy. Now note, this is not the exact same sample, as you'll see. So you run this. Now, this time there are 37,040 people, and unlike before, where 6,000 of them were used in the analysis, this time 37,000 were used in the analysis. So this is a much more representative and larger group than the previous one. And we see that our F value is pretty enormous. Probability less than 1 in 10,000 of getting this by chance. Our R squared is about 5%, so about 5% of the household income is predicted, see our label here, household income, is predicted by whether or not the spouse, the woman in the family, is literate. And you can see again, here's our label, mom literate, household income, and here's the household income where the mother's literate, and here's the household income where she is not literate. Now, don't go beyond your data here. This is a mistake that people make all the time and say, well, if you marry a woman who's literate, obviously your income will be higher. Not necessarily at all. My presumption is that men who are literate are more likely to marry women who are literate, and they are more likely to be the breadwinners in these homes in India. And so it's not necessarily the wife being literate, but that the wife, again, goes back to that common variance. Though it would be an interesting study to see if there was an interaction effect or if the woman being literate added to the explained variance. Remember how we looked at that at the two-way analysis variance before? So that would be interesting to see. And we'll go through more of these examples in the course. Down here, we only have two groups, right? And it says that means with the same letter are not significantly different. So here is the mean income for the household where the wife is literate, and their mean income in rupees is 123,000. And for households where the wife is not literate, it's 81,000. They have different letters, so these two are different, which you could have also guessed because the F was different and there were only two groups here. Alrighty, so now we have done two different one-way ANOVAs. Let's put them together and do a two-way ANOVA. So the mean statement here gives you the means and a Tukey post hoc test. Now we're going to do a proc GLM again, data equals example, class. I'm going to put both of the independent variables, the categorical variables in my class statement. And I've got model income equals literacy, how far apart you plan your children, and the interaction of those two. And then I'm just going to use a mean statement because I'd like to see for each of those 6 categories what the means are. So I'm going to run this. And here you see I've got 2 groups of literacy, yes or no, 3 groups of family planning, less than 2 years, 2 years or more, let God decide. There are only 6,184 variables used because we didn't ask the family planning question, everybody. Here we see the model sum of squares has an F value of 85.99, so about 86, highly significant. This says that your model, that these variables predict or explain income, is significant, but it doesn't tell you that every one of them is significant. So I have an R square of about 6.5%. About 6.5% of the variance in income is explained. But look here. So with literacy, that is again highly, highly significant, really ginormous F value. Family planning, not at all significant, tiny little F value. And the interaction of the two, not at all significant. So what it says is literacy of the mother is related to your income. I say mother, but I guess they don't all have children, but most of them did. Almost all of them did. So the literacy of the woman in the home is related to income, but how far apart you plan to space your children is not related to income. And whether you're literate or not, it's still not related to income. So my hypothesis was completely wrong. When I look at the plot of my means here, so these are the 3 groups where the mother is not literate. If they planned on having a new baby in less than 2 years, more than 2 years, left it up to God, they all had lower incomes than the 3 groups where the mom was literate, whether she planned on having a baby in within 2 years, more than 2 years, or who knows. So I included this in part because I think people often think that, well, if I do enough different analyses, my hypothesis will come out. Not necessarily at all. And really, it's probably not surprising because I am not an expert on the relationship of fertility to income in India, so it would be kind of surprising if my hypothesis came out. But that's how you do it. So that's enough review for now.